Alrighty, good morning, lads and ladies. Welcome back to MAP2302. Today is a cool day for us because we're finally going to use the Laplace transform to solve a differential equation. For a lot of people, the Laplace transform is sort of the only way they would consider solving constant coefficient linear differential equations because it kind of lets one machine do everything, and it has this magical ability to boil a calculus question down into an algebra question. And computer algebra systems have become endlessly more powerful in the last 20 years. I'll tell you, when I started college, there were really only two out there, Maple and Mathematica, and I don't have it easily within reach, but the user manual for Mathematica, which is what I used when I first started exploring these things, is about this thick, requires learning, a whole new programming language, and it's frankly very intimidating. Since then, packages have been developed for Python and a lot of other more user-friendly programming languages. Maple and Mathematica are still around. Maple is kind of the gold standard now. And packages have been developed for R and for other languages that have utility outside of mathematics. All of these things are very, very good at solving algebra problems, specifically linear algebra problems like inverting matrices, solving systems. And that's essentially what the Laplace transform does. It turns a differential equation into, a linear algebra problem. So by being able to take something from the domain of calculus, where computers are not great, they're good, don't get me wrong, but they're not great because calculus always involves this kind of notion of infinitesimal or infinity, arbitrary closeness, small epsilons, things like that, which humans can reason with pretty well if they train on it. Computers are discrete. They deal with chunks. They don't deal with continua. So by being able to take something from the domain of calculus, where computers are not so great, to the domain of algebra, where computers are incredibly powerful, we're able to resolve a lot of things kind of quickly. And for many, many engineers in particular, the Laplace transform, because of its ability to do that, is the preferred way to solve the sort of differential equations that we've been working with for the last few weeks. Okay. A few things before we actually do this that we need. Let's get started over here. At this point, we now know how to calculate the Laplace transform of a function. Oh, it's today. Today is the 29th. So we know how to calculate the Laplace transform of a given function, a known function. We know how to take inverse Laplace transforms. And well, for us, the idea of an inverse Laplace transform is a fairly simple thing where you take the transformed function, the f of s, and you break it up into nice little pieces, and then each one of those, hopefully you just know the inverse Laplace transform for. In general, that can be a tricky biscuit. We're going to restrict our attention to those cases where we kind of know what to do. But inverting integral transforms is one of those special things, and I invite you to explore that with other integral transforms like the Fourier transform. So we know how to do the forward transform. We know how to do the backward transform for a reasonable class of functions. If we're going to use the Laplace transform to solve a differential equation, we need to know how to take the Laplace transform of a differential equation. So that's the big goal for today. Today we're going to learn how to apply Laplace transform to a constant coefficient linear ODE. And you might say, but John, I mean, we already know how to solve constant coefficient linear ODEs. Yeah, yes and no. You have solved many of them, but the whole thing hinges on your ability to find the roots of a polynomial. That is a hard algebra problem, turns out, right? Finding the roots of a polynomial, if the polynomial factors nicely, i.e., most of the roots are rational numbers, then sure, yeah, we've got the tool, right? The worst case scenario, we've got our rational roots theorem. We can check the synthetic division by looking at divisors of the constant over divisors of the lead coefficient. Fun story. When I learned about the rational roots theorem way back in pre-calculus, I remember going, oh, well, now I can factor everything. And with one of my friends from class, went home, put a just random polynomial on the whiteboard, right? Just chose coefficients at random, integer coefficients at random. And we spent quite a while trying to factor it. We're like, okay, well, let's break out the rational roots there and let's just see, we should be able to do this now. We discovered through synthetic division that even looking at the many, many combinations of P over Q things and checking through synthetic division, that none of them worked. None of them worked. And it was very frustrating. And we sat for a long time trying to figure out what we'd done wrong, because we have this tool now, we should be able to factor everything. And only after going back and rereading the theorem did we understand what went wrong. What went wrong is that the rational roots theorem, show you. Wikipedia page might be better. Just need the statement of the theorem. Just need the statement of the theorem. Just need the goddamn statement of the theorem. This theorem states that each rational solution of this polynomial equation in lowest terms satisfies the following. The way that I always phrase this when I teach it to students is, if this polynomial has any rational roots, then they will be of the form P over Q, blah, blah, blah. That if is a big hypothesis. Turns out you really need that. Many polynomials don't have rational roots at all. Many even simple polynomials, x squared minus 2, have roots you can find, but they're not rational. So the rational roots theorem is only good at detecting roots that are like fractions made out of whole numbers. And that's where we went wrong, because by writing down a random polynomial, we'd written one down that didn't have any rational roots. And it turns out, if you write down a random polynomial with integer coefficients, odds are it's not going to have any rational roots. As a math teacher, someone who has to frequently come up with questions, selecting the polynomials to ensure the roots are rational and therefore factorable using the tools we teach is in itself a challenge. You kind of have to work backwards. So that's the issue, right? You can solve a constant coefficient linear differential equation using the tools I've given you so far, if and only if the auxiliary polynomial has rational roots, or at least all but 2 of the roots rational. You can factor the thing. The Laplace transform doesn't give a shit about that. It does not care. So that's the magic here. The Laplace transform will broaden the class of constant coefficient linear differential equations that you can solve. Even if you can't factor that auxiliary polynomial and use the other tools, the Laplace transform, because it just works differently, will reduce the calculus problem to a different algebra problem. And that algebra problem, being a linear algebra problem, is a lot more tractable. So that's kind of the ethos. Okay, big idea. Given an ODE of this, of the form an times the nth derivative of y plus an minus 1 times the n minus first derivative of y down to a1 y prime plus a0 y equals g of x, we will apply the Laplace transform to both sides. All right. Because of the way the Laplace transform interacts with derivatives, the left-hand side will become an algebraic expression. And that's the big thing I have to show you today is how the Laplace transform interacts with the derivative. As I do this, I'm assuming that y prime, y double prime, all the way out to the nth derivative of y, I'm assuming that all of these functions on the left-hand side, which are, remember, unknown, that's what I'm trying to find, are of exponential type. I have to assume that that growth condition from the end of class last time is met in order to say that I can take the Laplace transform. So that there is a baked-in assumption there. Other kind of catch here is that it's not just ODEs, really. We need initial conditions. When you take the Laplace transform of a derivative, it doesn't just spit out like S's, it also spits out constants that relate to the initial conditions. So it's really an IVP thing. The left-hand side, however, will become an algebraic expression, as will the right. One of the terms on the LHS will be capital Y of S, which is the Laplace transform of little, or what we've been using. I'll just leave off the variable. The Laplace transform of the solution. So we will, right? So we will solve for Y of S. Then invert the transform to recover Y. All right, that's it. That's the big idea. So we get an algebraic equation. One of the terms that's in that algebraic equation is the Laplace transform of your solution function. You rearrange things until you've got the Laplace transform of your solution equals some shit. And then you take the inverse Laplace transform on both sides. And that means the left-hand side over here is now the inverse transform of capital Y of S, which is little y, your solution function. And on the other side, you have the inverse Laplace transform of all that shit. So if you can invert the Laplace transform of all that shit, then you get your solution function. It's beautiful. It's really beautiful. And it's kind of shocking. So yeah, let's do it. Like I said, we need to know how to take the Laplace transform of something that looks like this. You know how to take the Laplace transform of something that looks like this, a constant times a function. And you know that if I add up a bunch of things and I take the Laplace transform, then I can just take the Laplace transform of each one individually. That's the linearity condition we proved yesterday. So what we need to know is, how do I take the Laplace transform of this, y prime, or the next term in here, y double prime, or the n minus first or nth derivative of y. I'd really like some nice way to express the nth derivative of y. Laplace transform, the Laplace transform of that derivative. Rather than stating it as a theorem, let's look at what L of y primed should be. And I'm gonna assume that this is a function of t. Again, so rather than writing x is for my independent variable, t will be my independent variable. And for reasons you'll see, it's nice to use the function notation. Instead of just calling it y prime of t is smart. So let's see what this looks like. All right. Well, kind of naively diving in, the Laplace transform of y primed of t should be the integral from 0 to infinity of y primed of t times e to the negative st dt. That's just the definition of the Laplace transform. This is an equal sign. My pen just smeared. And if there's one integration method we've seen again and again show up in this course as critical, its integration by parts. So you won't be surprised to know the way I'm going to kind of grapple with this is using IVP. But remember also, we need to be careful about the improper integral. So I will write this as limit r to infinity, integral 0 to r, y primed of t, e to the negative st dt. And it's to this that I'll do some integration by parts. Remember, my goal is to get an expression involving y of s, the Laplace transform of little y. So I would like to turn this y primed into a little y, because if this were a little y instead of y prime, then this would be the Laplace transform of y. So to turn the y prime into a y, I'm going to pick that for my dv. All right, I want to integrate the y primed to turn it into a y. So dv is going to be y primed of t dt. And that means u, my choice of u, is going to be e to the negative st. It's got to be everything else. From here, we calculate du, which would be e to the negative st divided by negative s dt. I'm sorry, du, we're differentiating. Sorry. What have I done? Differentiate. Negative s. Yeah, not integrate. Okay. And then to pass from dv to v, we need to integrate. If you integrate y prime, you get y. And I'll write it as y of t. Okay. So that's my integration by parts. I'm going to continue this over here. So I'll have lim r to infinity, and then I'll open up a big parentheses because I'm about to replace that integral by a whole bunch of integration by parts stuff. We're going to have u times v, so that's e to the negative st times y of t. And that gets evaluated from 0 to r minus the integral from 0 to r of v du. So that's going to be, all right, I'll just write it as it is, y of t times negative s e to the negative st dt, and then close that big print. Okay. From here, we can evaluate this. I can pop out this negative s factor here and see what we get. So this is equal to lim r to infinity. Open big prime. Now I'll take the chunk here and evaluate between bounds. Remember, we're plugging in for t. So this is e to the negative sr times e to the negative sr times y of r minus e to the negative s times 0 times y of 0. Well, e to the negative s times 0, that's e to the 0. So this is just going to be minus y of 0. Maybe I'll put that in some little brackets or something. Okay. And then from here, I'll still have this guy. I can pop out the plus s integral 0 to r. And then we have y of t times e to the negative st dt. Okay. Now, there is a bit of a sticking point here. Remember I said that I'm assuming the y function is of exponential type. So as r goes to infinity, what that means is I'm assuming this guy is capable of dragging this whole expression down to 0. And that's not obvious. I hope it's clear that this is an issue. But I aim to go ahead and take this limit. And if I'm going to do that, then I need to know something about the function y of r. I need to know whether this, grows so quickly that this thing going to 0 doesn't have an effect. So if the y of r function were to go to 0 with r, sure, that that's easy. I can say, okay, definitely that limit would be 0. If the y function grows like a linear function, it goes to infinity, but goes there slowly, I could still say, okay, this product would be 0 because we know the exponential overwhelms. Because we're assuming the y function to be of exponential type, we are then safe to go ahead and say, oh yeah, all right, this definitely then is going to be 0. And that's sort of the catch. As you can imagine, this is going to put a little bit of a constraint on the type of differential equations we can solve with this, but since, so I'll say this goes to 0, since y is of exponential. Then if I send r to infinity here, this just becomes an improper integral again. So what I get is negative y of 0 plus s times the integral from 0 to infinity y of t e to the negative st dt. And the hope is that you recognize the object on the far right. What is this?
It's just the Laplace transform.
It's the Laplace transform of the function little y. Yeah. So this is negative y of 0 plus s times capital Y of s. Where remember the notation we use, the Laplace transform of little y of t, we call big Y of s, right? The Laplace transform of little f of t is big F of s. The Laplace transform of little function of t is big function of s. And usually people write this kind of the other way around. S big Y of s minus y of 0. So good news and bad news here. Good news is, yeah, we can do the calculation. Bad news is it comes out in terms of y of 0. Now, you don't just get the Laplace transform of y, you also get this y of 0 term. And that's what I meant when I said, well, we really use this to solve initial value problems. So if you've got an ODE that you want to solve through Laplace transform, really you need to impose some initial conditions in order to be able to use the Laplace transform. Good news is every application problem is an initial value problem. When you're dealing with a physical system, that system always starts in some condition. Those are in some state. Those are your initial conditions. All right. So what is this? I.e. the Laplace transform of y of t, sorry, y primed of t is s y of s minus little y of 0. Next, we're going to look at the Laplace transform of y double prime, and then I'll give you the result in general. Next, we find the Laplace transform of y prime prime of t. And as you've seen, most of the differential equations we solve are second order. It's because harmonic oscillators, even damped harmonic oscillators, even driven damped harmonic oscillators are described by order 2 equations. So those are sort of the most important things for understanding like electromagnetism, resonance phenomena, all that good stuff. Okay, let's do it. So the Laplace transform of the second derivative of y is the integral from 0 to infinity y double primed of t times e to the negative st dt. And if you'll forgive me here, I am going to get just a little bit hand wavy. I'm not going to write out all the limit stuff. When I use an assumption to clear a limit, I will tell you what that assumption is, but I'm just going to go ahead and do the IVP with the assumption that this integral converges. As before, my goal is to kind of move the derivatives closer to the original function because I want to get big Y of S out. So that means I want to integrate the Y double prime term. So I pick that from my dv. And I want to differentiate the e to the negative st. So that means du is negative s e to the negative st dt. And v, the integral of y double prime, is just y prime. Right, so there's my by parts table. And what comes out of this is u times v. So y prime of t times e to the negative st evaluated from 0 to infinity minus the integral from 0 to infinity of v times du, which is y prime of t times negative s e to the negative st dt. As before, at infinity, I'm going to assume that this guy is not so large that he can't be dragged to 0 by e to the negative st. So this first piece here is going to give me 0 minus, and then when I plug in 0, that's y primed of 0 times e to the 0, which is just y primed of 0. And here I'm again assuming this comes from assuming y of t is of exponential type. And then the object over here, again, I can pop out a negative s and I'll get plus s times the integral from 0 to infinity y primed of t e to the negative st dt. And I could, if I wanted to, I could run integration by parts on this again. But you recognize it as the same integral we did earlier. This is the Laplace transform of y primed. So let's state it like that. Save ourselves some work. This is negative y primed of 0 plus s times the Laplace transform of y primed of t. So again, kind of an inductive thing going on here, like we talked about yesterday. The Laplace transform of y primed, that's the thing we computed a second ago. It's this. So I'm going to plug s y of s minus y of 0 in here. And of course, we do that in parentheses because it's a difference of two terms. So this is negative y primed of 0 plus s times s y of s minus y of 0. And rearranging, I'll get s squared times y of s minus s y naught, or sorry, minus s times y0. And then I've also got this y prime of 0, so minus s times y of 0 minus y prime of 0. And that's it. That's the Laplace transform of y double prime. Okay. And there's a pattern starting to develop. Let's see, should there have been a minus somewhere that I lost? Let me double check here. No, this is good. A pattern will develop. All right, pattern will indeed develop. Every time you take the Laplace transform of a higher derivative, you'll do one run of integration by parts. You'll get the next derivative down, evaluated at 0, but with a negative. And then you'll have s times the Laplace transform of that next derivative down. So let me recap what we have here so far in a place, because this is the thing you're going to need to refer to often. Sketch this over here. The Laplace transform, and this is all you need for second order equations. Laplace transform of y double primed is s squared capital Y of s minus s times little y of 0 minus y primed of 0, and the Laplace transform of y primed is s y of s minus y of 0.
Professor, I have a question.
Mhm.
So if it was to be to the third derivative, would it be something like s squared, cubed, y of s minus s squared y of s, and then minus sy of 0, and then minus y to the third derivative of 0?
Almost. So if you kind of compare these two, you can come up with the sort of generalization that you're looking for. The Laplace transform of the second derivative has an s squared times the Laplace transform of y. So the Laplace transform of the third derivative, s cubed, y of s. And then below that, what you see is here an s times y of 0 minus no s times y primed of 0. So what you see is that the power of s's go down, and you start with the Laplace transform, then the function, and then the derivatives go up. And these are like conditions, right? Constants. So let me go ahead and write down the, what do you call it? The functional equation. Generally, we can see, or we can calculate L of the nth derivative of y in terms of L of the n minus first derivative of y as follows. L of the nth derivative of y, that would be integral 0 to infinity, the nth derivative of y times e to the negative st dt. And by running IBP with u as e to the negative st and dv as the nth derivative of y, du is always going to be that negative s e to the negative st, and v here is going to be just one derivative less, y n minus 1 of t. So this would give me u times v, so e to the negative st times y n minus 1 of t, evaluated from 0 to infinity, minus the integral from 0 to infinity of, can I just write the plus s, or bring that negative s out, and then you have here y n minus 1 of t e to the negative st dt. We recognize the object on the far right as the Laplace transform of the n minus first derivative, this guy. And we recognize this over here, again, assuming that y is of exponential type, as being negative y n minus 1 of 0. And then here plus s times the Laplace transform of the n minus first derivative. So this is kind of like a recursion, if you want to think of it that way. It tells you how to get the Laplace transform of the nth derivative in terms of the Laplace transform of the n minus first derivative. You can induct on this to prove the following formula. You know, just do the same thing to the object on the bottom right, and it would pop out. So my keyboard's hooking up. If I kind of do this again to this thing, it would pop out another term that looks just like this, only it would have y n minus 2 and y n minus 2 here. So inducting on this yields, no, I'll give you the full formula. The Laplace transform of the nth derivative. Now it's going to be a big long sum. Of course, it's going to have many, many terms, I think more than n terms, and maybe n plus 2 terms, definitely at least n. This will be s to the n times the Laplace transform of y, which we write as big Y, minus s to the n minus 1 times y of 0 minus s to the n minus 2 y primed of 0. So it's like we were saying, the powers of s go down as the derivatives go up, and this will continue minus all the way down to the last term, which is just y, the nth derivative, or sorry, n minus first derivative of y evaluated at 0. So there's, I'll write the last two terms, s y n minus 2 of 0 minus y n minus 1 of 0. Now it's very rare you'll need anything other than the two that I put at the top there. All right, most of the equations we solve are second order, but some are third order, some are fourth order, you know.
Can you zoom out so I can see both those equations on the top? Thank you.
Sure, yeah, here's everything. So the two in the box at the top, this will handle most of the stuff you're going to see, because most of the stuff we deal with is second order. But if you need a third or fourth or fifth order, for whatever reason, this formula will do the job. And the way to remember it is kind of like what I think Malin was conjecturing out there. The Laplace transform of y triple primed, you know, for example, according to this formula, would be s cubed times the Laplace transform of y minus s squared times y of 0 minus s times y primed of 0 minus y double primed of 0. So you start off with s to the n times the Laplace transform of y, then the power of s's go down as the derivative of the initial conditions go up. So 0th derivative, first derivative, second derivative would be next, third derivative, n minus second, n minus first. What you see is you need these initial conditions, right? Without these initial conditions, everything's, you know, you're in trouble, because you'd have all these unknowns. But if you know y of 0, y primed of 0, the second derivative evaluated at 0, and so on, then you can actually calculate this, this Laplace transform quite concretely. And the term you're going to try to solve for is the capital Y of s. You'll have taken the Laplace transform of the left and right side. You will solve for y of s, then invert the Laplace transform. Now, the inversion process leans heavily on partial fractions. You guys ready to do it? Okay, let's do it. Let's take the Laplace transform of the initial value problem. We're going to keep this one easy, so we get a feel for the mechanics. Solve the IVP y primed of t. I'm going to write the t's just to remind us, because it's easy to make mistakes there. Plus 3y of t equals 13 times the sine of 2t. So this is a first order IVP. God knows we could have solved this a while ago. But let's solve it with the Laplace transform. So what I need here also are the initial conditions. I need to know what y of 0 is. So assume y of 0 is 6. We're going to do it by Laplace transform. So I'm going to take this equation, the ODE, and apply L to both sides. Use good notation here. Write the two L's on either side. Don't write L of the equation. That notation does not make sense. I know your hands get sore. Let me show you something fun. I don't know if you guys can see this. I'm not giving you the bird. This is where I peeled a massive callus off my middle finger from writing so much the last few years. So it's one of the, it's like guitar players having calluses on their fingers. Be proud of it. You write alone. All right. First, I'm going to use some properties of the Laplace transform to break these up into individual things that I know how to handle. So this is the Laplace transform of y prime of t plus 3 times the Laplace transform of y of t equals 13 times the Laplace transform of sine of 2t. And each of these Laplace transforms are known quantities to us. I'd like to start on the right-hand side. Who remembers the Laplace transform of sine 2t? That was the imaginary part of 1 over IA minus s.
It'll be 2 over s squared plus 4.
I think that's correct. Double check my own notes just to make sure it's. One of them has the s upstairs, one of them has the 2 upstairs. I think you're correct, so I just want to make sure. Yes, you're correct. Okay, so this will be 13 times 2 over s squared plus 2 squared, which is 4. And on the left-hand side, the Laplace transform of y of t, we know that's capital Y of s. And the Laplace transform of y prime of t, that's the thing we just calculated a second ago, that's s y of s minus y of 0. So applying the Laplace transform to both sides, we end up here. And you see what I mean, right? This is an algebra equation. My goal is to isolate y of s. It shows up twice, so I'll have to combine those terms. I also have here this y of 0. And that's why we need to have initial conditions to use the Laplace transform to solve. That's why we use it for IVPs. If you want to solve an ODE and you don't have initial conditions, just force some. Just fucking pick some, man. Y of 0 equals 0. Who cares? But in all the application problems, all the real world settings, you're going to have initial conditions anyways. Y of 0 is 6. So what we really have here, let's clean things up. S y of s plus 3 y of s is s plus 3 y of s minus y of 0 is minus 6. And over here we have, I'll leave it, that's 30. No, let's bring it up. 26 over s squared plus 4. All right. Remember what our strategy is. Take the Laplace transform, solve for y of s, then invert the Laplace transform. That'll give us little y. So the long game here is to get this alone and then inverse Laplace transform both sides. So I'm going to have to add 6 to both sides and then divide both sides by s plus 3. When I add the 6, the two terms over here won't have a common denominator, so I'll need to put those into a single fraction. But you see, it's all just algebra stuff, and that's what I mean. This is stuff computers do really well, really quickly. So this is going to be 26 over s squared plus 4 plus 6 quantity s squared plus 4 over s squared plus 4. So that's 6s squared plus 24. 24 and 26 we'll need to combine. So let's see what that numerator is going to be over there. 26 and 24 is 50, right? So the numerator here is 6s squared plus 50. And the denominator is s squared plus 4. And then when I divide over by this s plus 3, that will give me y of s alone on the left-hand side. Boom. So you see what we did here, without ever resorting to auxiliary equations or any calculus tricks really, besides taking the Laplace transform, which is in fairness a pretty deep and heavy calculus trick. But without any of that, I have arrived at the Laplace transform of the solution. It doesn't even feel like I solved the differential equation, but we really have. The thing is, the solution is just in a form that is fairly opaque. So to return to a form of the solution that I know how to handle, I need to invert the Laplace transform. And that's going to mean rewriting this right-hand side in a form where I can recognize the inverse Laplace transform. So what do I do with this object here? First, good place to pause. Any of these algebra steps we want to talk about? Anything, am I making any mistakes? Nobody see anything to worry about? God knows I do make mistakes. It looks pretty good to me. So then I'll ask you the question, what should I do to this in order to calculate the inverse Laplace transform of it?
We need to use partial fraction decomposition.
Very good, right? We need to split it up into a bunch of little pieces whose inverse Laplace transforms are known. So like if I just had, some constant over s squared plus 4, I know how to find the inverse Laplace transform of that. If I just had some constant over s plus 3, I know how to find the inverse Laplace transform of that. The catch here is that this doesn't necessarily decompose as some constant over this plus some constant over this. There's a little subtlety, and I'd like to know who remembers that little subtlety from Calc 2 or pre-calc.
It's with the irreducible quadratic, right?
Yes. S squared plus 4 is an irreducible quadratic. The roots of s squared plus 4 are not real numbers. They're plus and minus 2i. So here, the truth is you have options, 2 of them. You could factor s squared plus 4 as s minus 2i times s plus 2i, and then do the old-fashioned, like, easy peasy partial fractions thing. But you're going to have to work with complex numbers throughout that procedure. And you're going to need to be comfortable kind of going back to putting things into the real numbers at the end. It's not entirely obvious how to do that. Although I'll say this, it's also not very hard. It's very similar to what I did for you guys when we calculated Laplace transforms sine and cosine yesterday. The way that this is taught, both in pre-calculus and in Calc 2, is that an irreducible quadratic factor in the denominator, rather than getting a constant over that in your partial fractions setup, gets a linear term upstairs. So my variable here is s, I'll call it as plus b over s squared plus 4. And then the simple linear factor just gets a constant. Yeah, I'm sweating.
I'm cold.
Okay. So this is the step that we would call the partial fraction decomposition. And our goal is to find the constants a, b, and c. This object I know how to find the inverse Laplace transform, right? That's e to the minus 3t. You know, this constant will come along for the ride. This piece I would split up into two. There will be like the as over s squared plus 4 and the b over s squared plus 4. And one of those will be a sine, the other will be a cosine. But in order to get something useful out of it, we need to know those constants. In order to find those constants, we cross multiply by the whole denominator, right? So this is our common denominator, s squared plus 4 times s plus 3. When I multiply this by s squared plus 4 times s plus 3, the s squared plus 4s will cancel, and I'll get as plus b times s plus 3. And when I multiply this by s squared plus 4 times s plus 3, the s plus 3s will cancel. So I'll get plus c times s squared plus 4. And on the left-hand side, the whole denominator will cancel, and I get just this top, 6s squared plus 50. So Arthur Mathick, when he delivers this lecture from MIT, says this is the real reason we taught you how to do partial fractions. It wasn't for the silly algebra problems in pre-calc. It wasn't for the silly integrals in calc 2. It was so you could find inverse Laplace transforms. That's what we had in mind the whole time. The truth is all those things are important. From here, things go a lot like the method of undetermined coefficients. You would blow everything apart on both sides and then set coefficients of s squared equal to each other. Set coefficients of s equal to each other. Set constants equal to each other. Before that, though, we can do some other stuff. In fact, I'm going to show you smarter, faster ways to do things. One of these is called the Heaviside method. And you saw me do that the other day where I sent s to -3. I'm going to do that again here. What you want to do is nuke as much as you can on one side. Nuke as much as you can on the right-hand side at a given time. So I'm going to take values of s that will like kill this whole thing. And if I could, I would take values of s that kill this whole thing separately. And if I'm able to kind of get all but one term to go to 0, then I can read off the constant associated with that remaining non-zero term. Excuse me. No. Again, there's no real number s that's going to nuke this. But if I send s to -3, then this will become 6 times -3 squared plus 50 is equal to, this whole thing is going to be 0. And then over here, I'd have c times -3 squared plus 4. -3 squared is 9 on a good day. 9 times 6 is 54 plus 50 is 104. So 104 is equal to c times 3 squared is 9, 9 plus 4 is 13. And this tells me that c is the somewhat unpleasant number, 104 divided by 13. 104 is not a multiple of 13, right? I don't think so. 4 divisible by 13. Let's see. 2 times 52. 2, 6. Oh, it is. Yeah. 104 divided by 13 is an integer. Because 104, let's see, 104. Sorry, my arithmetic is embarrassingly bad. This is 2 times 52, right? And then that's 2 times 26. And so that's 8 times 13, is that right? So the 13 cancels and you just get 8. Okay, so C is 8. We still need to find A and B. And there are fast ways and slow ways to do this. The big deal here, kind of this equation is our sort of master equation for this process. So I'm going to go back here and multiply things out and equate coefficients. Throughout that process, I'll be mindful that C is 8. So kind of returning to that blue equation. We have 6s squared plus, all right, 0s plus 50 is equal to, if I look for the s squareds on both sides, I see here I'll have as times s, that's as squared, plus cs squared, and that's all the s squared, so I would have a plus c, but c is 8. Maxie, no. Sorry, this new puppy we got sitting on that dog bed right next to me. A plus c, which is a plus 8 times s squared. Linear terms. Yeah, it's surprised it's on that. Maybe just everything on top of this in the wash. Linear terms here would be, let's see, I'll have 3as from this, and then plus bs from this. So that's 3a plus b times s. No linear terms from this. And then constant terms from the first group here, I'll have 3b, and from the other guy, I'll have 4c, so that's plus 3b, and then 4c is 4 times 8 is 32. All right. So using c equals 8, expanding everything on the right-hand side, and then recollecting powers of s, that's what I've done here. What you just saw me do is the smart way to do that, right? Rather than like taking the time to FOIL everything out, you just ask, what s squared terms do I get from this? What s squared terms do I get from this? And then write them down. What s terms do I get from this? What s terms do I get from this? And then you write them down. What constant terms do I get from this? What constant terms do I get from this? And then you write them down. All right. I have 6s squared on the left and a plus 8s squared on the right. So a plus 8 must be equal to 6. I have 0s on the left and 3a plus bs on the right. So 3a plus b that better be equal to 0. And I have 50 as the constant on the left, and 3b plus 32. I'll put a dash here because it's a similar color, isn't it? So my final equation there is 3b plus 32 equals 50. These first two are actually enough for us to solve for a and b, but this guy will make things a little bit faster. So I can arrange these in a system, a linear system. That's what I meant when I said that the Laplace transform takes the differential equation and turns it into a linear algebra problem. So a plus 8 is equal to 6. 3a plus b is equal to 0. And 3b plus 32. 50. You will always arrive at a linear system through this procedure, and you need to solve it. And if you're lucky, you're smart, you use this trick to get at least one of the coefficients early, and hopefully you can get more. Maybe you can get all of them. Sometimes you can. That way, the linear system you get is, the term we use is sparse, not hard. So here you just have a and constants. So I can read a off right away. A is -2. And from the bottom one, 3b is 50 minus 32, which would be 18. So b is 18 thirds, which is 6. We don't even need the middle equation. right? So I've got A, B, and C. This means y of s, which was 6s squared plus 50 over s squared plus 4 times s plus 3 is secretly negative 2s plus 6 over s squared plus 4 plus c was 8 over s plus 3. I.e. y of s is negative 2s over s squared plus 4 plus 6 over s squared plus 4 plus 8 over s plus 3. And now we need to take the inverse Laplace transform of both sides. And the trick to taking the inverse Laplace transform is going to be to kind of think carefully about what to do with these constants. In some cases, leaving one of them upstairs will be nice. In other cases, you'll want to replace them by other things, which will require baby algebra tricks. But let me just go ahead and say the result. Y of t, our solution, is the inverse Laplace transform of capital Y of s, which is the inverse Laplace transform of each of these, or say the inverse Laplace transform of that sum. So negative 2s over s squared plus 4 plus 6 over s squared plus 4 plus 8 over s plus 3. Inverse Laplace transform. Sorry. There we go. All right. So the inverse Laplace transform of 2 over s squared plus 4, I know that. The inverse Laplace transform of 6 over s squared plus 4 doesn't quite look right. If it was 2 over s squared plus 4, I'd be like, boom, cos 2t. But it's 6, so we need to think a little bit carefully about what to do there. And then the inverse Laplace transform of 8 over s plus 3 is going to be 8e to the negative 3t. So if we come down here, I'll write it like this. This is negative. Remember, constants pop in and out of inverse Laplace transforms. It's a linear operator. S over s squared plus 4, negative 2. Yeah. All right. So I pop the negative out from the first guy because I know the inverse Laplace transform of 2s over s squared plus 4. From the second guy, 6 is 2 times 3. So I'm going to pop out a 3. And what's left is the inverse Laplace transform of 2 over s squared plus 4, which I know. And then from the last guy, I'll pop out the whole 8 because I know the inverse Laplace transform of 1 over s plus 3. Does everybody follow what I've done here? Are there any questions about, I'm thinking this middle guy in particular is a little subtle. All feeling good? The idea is, I don't know the inverse Laplace transform of 6 over s squared plus 4. That's not something I recognize as a Laplace transform that I've calculated. But I do know the inverse Laplace transform of 2 over s squared plus 4. That's cosine of 2t, right? A over s squared plus a squared. So I write the 6 as 3 times 2, and I pop out the 3. Even if this was something totally different, like something that didn't have a factor of 2 in it, like 7, I would pop out the 7. And then multiply and divide by 2. So I'd have 7 halves times 2 over s squared plus 4. And then pop out the 7 halves, leave the 2 in. Let's go through it. What is the, so here's the negative. What is the inverse Laplace transform of 2s over s squared plus 4? Anybody?
It's going to be -2 cosine of 2t.
Very good. Cosine of 2t or sine of 2t? I always do this, right? You catch me doing this same. So I think that one is sine. Oh no, cosine, you're right. You're absolutely right. Oh, and the 2 needs to come out here also. Yeah. I'm so sorry. So really we should bring the 2 out also.
Actually, couldn't you use couldn't you use U substitution?
No, we're not integrating. We're taking
Oh.
the inverse Laplace transform.
Right.
If we were integrating, yeah, absolutely you should. But the goal here is to kind of recognize this as the Laplace transform of some known function. And I do recognize I was wrong to say leave the 2 in there. S over s squared plus 4, that's the Laplace transform of cos 2t. So I'm going to pop the -2 out. -2 cos of 2t. And the other one has the a inside. So this guy, 2 over s squared plus 4, that is the Laplace transform of the sine of 2t. So this will be plus 3 times sine of 2t. And then 1 over s plus 3, that is the Laplace transform of e to the -3t. So the inverse Laplace transform of that is e to the -3t. And what do you know? Here's your solution. There's no C1, C2, there's no free constants because it's an initial value problem, right? Initial value problems have unique solutions. No free constants in them. That's what we wanted. So we win. Good shit, right? And this is going slow and careful through pretty much everything. I'd like you to take a second and compare your notes to what I have here, because I did have to make a couple of corrections, right? The 2 coming out versus just the negative coming out. So compare your notes to what I have here, make sure that what you have matches what's on the screen. Are there any questions about where any of these pieces come from? I kind of can't believe that there are not. But again, the big thing here, take the Laplace transform of both sides, solve the equation for capital Y, then take the inverse Laplace transform. All the work is done by the Laplace transform. Inverting the Laplace transform manually, like, is there a formula for the inverse Laplace transform of a function? The answer is yeah, but it requires something called contour integration, which is another thing from complex variable theory. So the only way we're going to be able to handle these is by remembering forward Laplace transforms, so we can read off or remember inverse Laplace transforms. And that's, if there's one part of this that I would say is unappealing, it's that. But it's very quick. It's very, very quick. Last call for questions on this before I do another one. One thing that you have to be mindful of is the denominators here. We know there are other cases in partial fractions, like where you have an s plus 3 squared, and that could lead to like an s plus 3 squared here. We don't know how to find the inverse Laplace transform of something like that yet. So we're going to develop rules like the convolution rule and other tricks to help us with forward and inverse Laplace transforms. If you haven't started on the Laplace transform homework yet, I need to insist that you do so immediately after class so you don't get lost in the next lecture. I'm going to solve another initial value problem using the Laplace transform here. And then we are going to start talking about some slightly more in-depth features of L. Last call for questions on this problem. Okay. Let's do a second order one. Second order IVPs have two initial conditions, right? Y of 0 and y primed of 0. And that's convenient because you know that the Laplace transform of the second derivative has those two items show up in it, y of 0 and y primed of 0. So let's solve y double prime minus 3y plus 2y, 3y prime plus 2y equals e to the negative 4t, subject to the initial conditions that y of 0 is 1 and y primed of 0 is 5. Oh, the charts. All right, so I want to solve this subject to these initial conditions using the Laplace transform. I'll take the Laplace transform on both sides. I'll go ahead and apply the linearity rule right away. E to the minus 4t there, sorry. And remember, we're assuming that y is a function of t. I'm not writing the of t's here. We have to remember what the Laplace transform of the second derivative is. So look back at your notes. What is the Laplace transform of y double prime? S squared times capital Y of s minus s times y of 0 minus y primed of 0. Powers of s go down, y's start with the Laplace transform, and then build up in derivatives with the 0 plugged in. Then we have minus 3 times the Laplace transform of y prime, which is s y of s. I don't know why capital Y's are so awkward for me to write. S y of s minus y of 0. And then plus 2 times the Laplace transform of y. That's plus 2 times capital Y of s. That's the left-hand side. This is this. This is this. And the Laplace transform of little y is capital Y. The Laplace transform of e to the negative 4t is 1 over s plus 4. All right. So on the left-hand side, I'd like to gather all the y of s's together. I have s squared of them here. I have minus 3s y of s here, and I have plus 2 y of s here. So altogether, the capital Y of s has s squared minus 3s plus 2 attached to it. Other terms, minus s times y of 0 minus y primed of 0. So let's just start writing this down. Minus s y of 0 minus y primed of 0. I have plus 3 y of 0 here. And then on my right-hand side, I still just have 1 over s plus 4. Again, these are known. So y of 0, it's supposed to be 1. Y primed of 0 is 5. So this is negative s times 1 plus 3 times 1. So this is s squared minus 3s plus 2 capital Y of s minus s times y of 0. That's just minus s minus y primed of 0. That's minus 5. And I'll really try to make my 5s distinct from the s's. I know that's a frustrating thing. And then I have here a plus 3. Maybe my s's can get little tails. And on the right-hand side, still 1 over s plus 4. All right. So I'm going to push all this stuff to the other side, have a common denominator, divide everything by this, and then run some partial fractions. So this is, I'll have a plus s plus 5 minus 3. Minus 5 plus 3 is minus 2. So what this will become is s squared plus 3s plus 2 times y of s equals 1 over s plus 4 plus s, and then these two together made minus 2, so that'll become a plus 2. That's it. And if I want to have a common denominator between these pieces, that's going to have to be s plus 4. So I can take s plus 2 and multiply top and bottom by s plus 4 over s plus 4.
Professor, real quick on the left side, I think you switched from a minus 3s to plus.
Thank you. Thank you. Thank you, guys. I very much appreciate that. Thank you. Good catch. All right. Having a common denominator between these pieces, I treat this as s plus 2 times s plus 4 over s plus 4. So we'll have y of s equals, over here I'll have 1 plus s plus 2 times s plus 4 over the s plus 4. And then I'll divide also by this quadratic, which is s squared minus 3s plus 2. Just algebra. And I need to FOIL this, add the 1, see if anything factors, cancels, does nice stuff, factor this. So this is s squared plus 6s plus 8. So that's going to be s squared plus 6s plus 9. And then downstairs, s plus 4 is s plus 4. S squared minus 3s plus 2 is s, let's see, does that factor s minus 2, s minus 1? Is that right? I think so, yeah. And the top here factors as well, right? Yeah, that's s plus 3 quantity squared. Not that it matters, right? So the reason I'm checking to see if the top factors is to see if there's anything that will cancel with the downstairs. If there is, saves me life. It's not saves me life, saves me some work. But the top factors as s plus 3 quantity squared, and there are no s plus 3s downstairs to cancel with, so we don't need to think too hard about that. We do need to set up the PFD. This is the acronym I use for partial fraction decomposition. And in this case, we just have simple linear factors downstairs, no irreducible quadratics, no repeated factors. So I write it as s squared plus 6s plus 9 over s plus 4, s minus 2, s minus 1 equals A over S plus 4 plus B over S minus 2 plus C over S minus 1. And then I cross multiply to kill all the denominators. And I get that kind of master equation for the partial fractions, which is S squared plus 6S plus 9 equals A times, if you multiply both sides by this whole denominator here, the S plus 4s will cancel. So you'll have left over S minus 2 times S minus 1 plus B times, here the S minus 2 will cancel. So you'll have S plus 4 times S minus 1. And then on the last guy, you'll have C times the S minus 1s cancel, S plus 4, S minus 2. Now, because the right-hand side doesn't have any irreducible quadratic factors and doesn't have any repeated factors, I can actually recover all three of those constants using the Heaviside trick. So if I send S to 2, this term and this term will vanish, and I'll get B. We'll have on the left-hand side 2 squared plus 2 or negative 2, positive 2, yeah. 2 squared plus 6 times 2 plus 9 equals A times 0, C times 0. So all that's here is going to be B times 2 plus 4 times 2 minus 1. And this says, let's see, what is that? 4 plus 12, so 16. 16 plus 9 is 25 equals B times 6 times 1. So 6B, is that right? Yeah, okay. So B here is going to be 25/6. Put that in my pocket. Maxie, what are you doing? Oh. And we'll send S to 1 to get C, send S to -4 to get A. When I send S to 1, my left-hand side is 1 plus 6 plus 9 is 7 plus 9 is 16. And my right-hand side, this goes, this becomes, let's see, 1 plus 4 is 5, 1 minus 2 is 1, so we have 5C. And I see that C is 16 fifths. And then as I send S to -4, I will learn A. So -4 squared, I'll write this one out, -4 squared plus 6 times -4 plus 9 equals, I'll have this goes and this goes, so I'll just have A times what? -4 minus 2 is -6. -4 minus 1 is -5. So -6 times -5 is +30A. And on the left-hand side, we have 16 minus 24 plus 9. So, +16 minus 24 is -8. -8 plus +9 is +1. So I'll get A is 1 over 30. So now I have finished my partial fractions. And what we discover is that the Laplace transform of my solution function capital Y of S is A over S plus 4. So I'll just write it like this, 1 over 30 divided by S plus 4 plus B over S minus 2, that's 25/6 over S plus 2 plus C over S minus 1, which is plus 16/5 over S minus 1. And there's a 5 here again.
Professor, for C, when you're sending it to 1, wouldn't it be a -5C?
Well, it might be, let's see. So here, right? Sending S to -1.
Oh, you send it to -1?
No, I'm asking. So let's see. No, yeah, we're sending S to +1.
Yeah.
So
Send
on the left-hand side, let me just recheck everything just to be sure. So on the left-hand side, I'll have 1 plus 6 plus 9 is 7 plus 9 is +16. That's good. On the right-hand side, as I send S to +1, oh yeah, 1 minus 2 is -1, right? So this is actually a -5C. Thank you, thank you. I'll come back and insert this negative in front of the 5 here, and that will make this -16/5. -16/5. You're being very polite about my mistakes, correcting them only when they're about to cause trouble. I appreciate that. That's very sweet. Okay. I think we are now here. I think we have.
Professor,
Yes.
you also wrote S plus 2 whenever it should be S minus 2 under the 25/6.
Damn, that's no good. All right. Again, I'm both appreciative of your correction and your courtesy. Okay. Are we now happy? Do we have the Laplace transform of our function sorted out? Looks pretty good to me. Okay. Yeah, I think we're good. So now our solution function is the inverse Laplace transform of all this. Okay. And in each of these, I'll just pop the constant out because 1 over S minus A is the Laplace transform of e to the AT. So this would be inverse Laplace transform here, need the inverse. I'll write this step just so we have, this is 1/30 inverse Laplace transform of 1 over S plus 4 plus 25/6 inverse Laplace transform of 1 over S minus 2 minus 16/5 inverse Laplace transform of 1 over S minus 1. That is 1/30 e to the -4t plus 25/6 e to the +2t minus 16/5 e to the +1t. And that's the job done. This handles issues of like linear independence really nicely. It handles kind of a lot of those weird rules that you had to memorize back when we were using other methods. Beautifully, really beautifully. There's no like separate solve the homogeneous equation, then look for a particular solution. And you know, within both of the procedures, for those things, generally there's some weird cases you have to memorize and know how to work your way around. And even if you do all of that correctly, at the end you would have to solve for the constants, right? So you'd find, for example, here your two solutions, y1, y2. you'd have C1y1 plus C2y2, and then you'd have to find your particular solution, yp. Then you would put all those together into y of t, and then you would differentiate y of t, plug in 0 to both of those, set up a 2x2 system of linear equations, solve for the constants C1 and C2, and only then would you be done. Here it's kind of one machine that does the whole thing. Okay. So I am going to publish a new homework for you guys. I wanted to do that yesterday, but I just didn't have time. The new homework is going to extend from where we are now, right? So the current homework ends just about where we are right now. It's solving some kind of basic IVPs using the Laplace transform. The next few things we need to learn how to do is find the inverse Laplace transform of those other not so nice partial fractions pieces. Like what if this was s-1 quantity squared? We don't yet know whose Laplace transform is s-1 quantity squared. That's going to require a little bit of work. What's more, we want to know how to handle some very particular kind of input or driving functions like that Dirac delta function. So we need to know that as well. There's something called the exponential shift rule. That's very useful because it'll allow you to calculate Laplace transforms of products neatly. And then there's something called the convolution theorem. And that is also a big friend of ours because it relates products of functions with products of Laplace transforms, but it's not the obvious thing. So next time we'll begin working with that sort of stuff. Questions on what we have done here today? Okay, please work hard on this current homework set. Do not fall behind at the end. This and the next bit of material, which is power series, some of the hardest, most technical stuff in the course, right? So kind of everything so far, as long as you remember your basic rules from Calc 1 and Calc 2, you're fine. But here we're dealing with the more subtle things like improper integrals and power series. And those are sort of the more challenging topics from Calc 1, Calc 2. So don't slack off in these last couple weeks. Work very hard now and you will make it through okay. If you slack off now, though, it'll bite you. It'll bite you bad. It'll bite you on exam 3 and it'll bite you on the final. And just 2 little nips, one from each of those, is enough to do some damage to an otherwise really good term. So please sink in the time. If you know you're weak in one of those areas, talk to me. I'll help you, right? I've got lots of good resources for those challenging things. But yeah, that's it. That's all I got for you guys today. You now know how to use the Laplace transform to solve differential equations. So you are officially badasses. Go ahead and make use of that wherever you want, but feel good about it. Start with the homework, though. Start there. Okay, I'll see you guys. So today's Thursday, right? So I'll see you guys on Monday. And on Monday, we will take care of these last few tricky things with the Laplace transform. And then we're going to start on power series. Okay. Questions before we go? Alrighty then. Have a good weekend, guys. Be on the lookout. There is another homework set coming, and I'll see you on Monday.